We are still into finding the limit of functions as x approaches infinity. And we are concerned with horizontal asymptotes. Let us get the limit of x squared plus 1 divided by x minus 1 as x approaches negative infinity. Well, it looks like this will give us another indeterminate form, because the limit of x squared plus 1 as x approaches negative infinity is infinity. And the limit of x minus 1 as x approaches negative infinity is negative infinity. So this is an indeterminate form. So do not rush into conclusions. This is not equal to 1, this is not equal to negative 1, this is not equal to infinity. Now look at what I will do. Our rational function is just equal to this, x squared plus 1 divided by x minus 1 times a factor, and that factor is 1 over x divided by 1 over x. This is just equal to 1, and so multiplying 1 to our function does not change our function. And this will bring us to x squared times 1 over x. So you will multiply this to each of the terms in our rational function. So x squared times 1 over x is just x. 1 times 1 over x is 1 over x. And then this one, x divided by, or x times 1 over x is 1 minus 1 over x. Okay, so let us now find the limit of x plus 1 over x divided by 1 minus 1 over x as x approaches negative infinity. Okay, so this one, as x approaches negative infinity, is negative infinity. The limit of 1 over x as x approaches negative infinity is 0. The limit of 1 as x approaches negative infinity is just 1, and this one is also 0. So what we have here is negative infinity plus 0 is negative infinity, divided by 1 is negative infinity. So this means our function decreases without bound when x approaches negative infinity. So this is the graph of g of x is equal to x squared plus 1 divided by x minus 2. So what happens when x approaches negative infinity? Our function decreases without bound. So what we are seeing here is a function that does not have a horizontal asymptote. So this is the summary of what we did the previous 2 slides and this last slide. And what we saw is this. This is what we saw. And pay attention to the pattern here. So the limit of this function as x approaches infinity is 3 over 2. But look at our numerator and denominator. They have the same degrees. So if n is the degree of the numerator, of the function in the numerator, it's equal to 2. If m is the degree of the polynomial function in the denominator, it's also equal to 2. They have the same degrees. So that's one pattern that is revealed by this function. Now let us look at this. The limit of this function as x approaches in negative infinity is 0. Now look at the pattern here. The degree of our polynomial function in the numerator is 1. The degree of our function in the denominator is greater than the degree of the function in the numerator. So in this case, m is greater than n. In this one, the limit of our function as x approaches negative infinity is negative infinity. And pay attention to the degrees of our numerator and denominator. Our polynomial function in the numerator is a degree 2 function. Our function in the denominator is a linear function. And in this case, m is less than n. In the first 2 cases, we have horizontal asymptotes. So when the limit of a function approaches a particular real number, as x approaches infinity, what you have there is a horizontal asymptote. I will show a summary of what we discovered. Theorem 1.6, limit at infinity and horizontal asymptotes. So if we are given a rational function, I hope that you are not overwhelmed by this notation. That is how you write a rational function using math language. It's a polynomial function divided by another polynomial function. The degree of your polynomial function is n. The degree of your polynomial function in the denominator is m. And so by paying attention to those degrees, you can tell what is or what are the horizontal asymptotes of your function without evaluating the limit as x approaches infinity. So it's something like this. When the numerator and denominator have the same degrees, as x approaches infinity, it will approach a horizontal asymptote. What is the equation of that horizontal asymptote? Look at that. So you pay attention to this, to the numerical coefficients of the leading term. It's just a sub n divided by b sub n. Look at this, look at this. So the degree of our function here, the numerator and the denominator, is both equal to 2. And look at what we found out. As x approaches infinity, it approaches the line y is equal to 3 halves. And where is 3 halves here? Look at this. This is 3 and this is 2. 3 halves. When the degree of our numerator is less than the degree of our function in the denominator, the horizontal asymptote is the line y is equal to 0. And that is what we found here. The degree of our numerator is 1. The degree of our function in the denominator is 3. What we have here is a function whose limit as x approaches infinity is 0, and that is also your horizontal asymptote. In the last example, what we have here is a function where the numerator has a degree that is greater than the degree of the function in the denominator. So it does not give us a horizontal asymptote. Now, if your teachers want to talk about oblique asymptotes, that is their prerogative. But me, I will not talk about oblique asymptotes. I will stop here. Okay, so I will flash some rational functions, and you will tell me what is the horizontal asymptote of these functions without evaluating the limit as x approaches infinity or negative infinity. Just by looking at it, tell me the horizontal asymptote. So our numerator is a degree 1 function, okay? This one is also a degree 1 function, and so the horizontal asymptote is this, okay? It's y is equal to negative 4 divided by 2, and that is just equal to negative 2. The degree of our numerator is 0, and the degree of our denominator is 2. And so this is telling us that the horizontal asymptote is the line y is equal to 0. How about this one? The degree of our numerator is 3, and the degree of our denominator is equal to 1. And so this one does not give us a horizontal asymptote. I will show you the graph of each of these functions. For letter A, this is the graph. And where is the horizontal asymptote here? It's this. The line y is equal to negative 2. Y is equal to negative 2. This is the graph of our function in letter B. The horizontal asymptote is the line y is equal to 0. And for our last function, this is the graph. It has no horizontal asymptote. As x approaches infinity, our function decreases without bound. As x approaches negative infinity, our function increases without bound.